Before we get too far into the course, we actually need to review some math because we're going to need to use some of it when analyzing the algorithms that we're going to be discussing. Let's start by taking a look at some exponent rules. Now, you might already be aware of all of these, but I just want to do a small review to make sure that you're aware of these rules because, as I said, you will see some of these when we analyze algorithms. So let's start by looking at something like this, where we have x power a times x power b. For all these rules, we're going to assume that we have the same base. We just have different exponents. So here, we're multiplying these together. All we have to do is take the two exponents and add them together. So x power a times x power b is simply going to be x power a plus b. That's all it is. Now let's suppose we want to divide these two numbers. So we take x power a and we divide it by x power b. All we're doing here is just we need to subtract the exponents. So we would simply have x to the a minus b power. Now let's try something like this. So let's say I have x power a, and I take all that and raise it to the bth power. Well, this is the same thing as just multiplying the two exponents. So our final result here would be x to the a times b power, or x power a times b. Now let's say we do something like this. It's a little different, where I'm just simply adding x power n with another x power n. Well, just from algebra, this just simply is 2 times x power n. But the reason why I mention this is some people think that, well, since it's x power n, you're adding to each other, that should be x to the 2n power, right? But no, this is completely incorrect. This is not right at all. It is going to be 2x power n. This is the result whenever we add x power n with itself. Now, why do I mention that? Well, let's take a look at this last rule right here. 2 power n, we add it with itself. We're actually going to see this in several cases in our algorithms. And what we find here is from our last rule that this comes out to be 2 times 2 power n. But what is that? Well, if we look at our first rule, so if we look at our first rule right here, what we see here is that we're multiplying 2 power 1 with 2 power n, because we can think of this 2 times 2 power n as simply 2 power 1. So think there's a 1 right there, times 2 power n. So we just simply add the two exponents, and we get 2 power n plus 1 as our final result. We'll next take a look at what are called logarithms. Now, you may have done absolutely nothing with logarithms before, or you may have done a little bit with it in your high school algebra class. But this is an operation that's commonly used in analyzing algorithms in computer science, especially when we start taking a look at algorithms where we actually divide a problem into smaller and smaller subproblems. Now, in computer science, when we talk about logarithms, there's usually a base associated with it. So all logarithms in computer science are of base 2, unless we say otherwise. So what you might have done in other classes is doing log base 10, but in computer science, we look at log base 2. And the reason why we do that is, if you remember before, whenever we're dealing with the ones and zeros and storing stuff in memory, that's binary, so that's base 2. So when we deal with logarithms, we're looking at base 2 logarithms. Now, what's the definition of a logarithm, or the operation? Well, let's suppose we have x power a, and we say that x power a equals b if and only if log base x of b is a. You can think of the log operation as kind of being like an inverse to exponents, is a way that I usually try to describe it. So if you have x power a and that equals b, well, log base x of b is a, the exponent. So we can use this as a way of, if we need to find the exponent of something and you know x and you know b, well, we can do log base x of b of that, and that would give us the exponent. So we're going to see how this is useful in several circumstances. So there are some log rules that we need to take a look at. So one of them would be, let's say I have log base a b. Well, how can we compute that? Well, the way we can get that is if we have some other base c, I can do log base c of b and divide that by log base c of a. Now this is assuming that a, b, and c are greater than 0 and a is not 1. So why am I talking about this? Well, let's say you're asked to compute log base 2 of 5. And how do you do that on a calculator? Because on a calculator, you don't do log base 2. I think if I remember right, all calculators have log base 10. So what you can do is you can take log base 10 of 5, divide that by log base 10 of 2, and that gives you log base 2 of 5. So that's why we're mentioning this particular rule. And then another one that we'll take a look at, and this one's actually pretty common in other circumstances, is if I have log AB, so I have the log of some product. Well, that's just simply going to be log of A plus log of B. Now here, once again, we're assuming log base 2, but this actually applies to any bases that we want. So as long as A and B are both greater than 0, if I have the log of some product, I can just split up the product, but I add the two logs. So log AB is just simply log A plus log B. We're next going to take a look at what we call the series, or a sum of a sequence of numbers. So we're going to go over some different types of rules, and we're just pretty much getting the sum of a group of numbers. So let me show you one example, something like this. Now you may have never seen this notation before, so let me explain what we have here. So let's start with the very first thing, this part right here, if I can draw a line. Okay, close enough. So the first symbol is the capital sigma symbol, if you're not familiar with the Greek alphabet. And this symbol represents the sum. So some people also call this the summation notation as well as the sigma notation. And what we're seeing here is we have some I that we start as 0, and we're going to go up to n. And we have basically n numbers here that we're going to add. You can kind of think of this almost like a for loop, where we say for I is 0, I is less than or equal to n, I plus plus, and then inside the body here, we're going to take the sum of some item. And this first number to the right of it, this 2 power I, this is what we're getting the sum of. So you can kind of think of that as being in the body of our loop. So this would be like sum plus equals 2 power I. So another way we can rewrite this is we're simply doing 2 power 0 plus 2 power 1 plus 2 power 2 all the way up to 2 power n. So that's what this notation on the left is doing. All we're saying here is if we added up all these powers of 2, this simply comes out to 2 power n plus 1, and then we subtract it by 1. That's all we're saying here with this first rule, this first series. Let's take a look at another one. So we have here the sum from I is 0 all the way up to n, a power I. So instead of looking at just 2 power I, now we're generalizing that to a. And this actually comes out to a to the n plus 1 power. Take that, subtract it by 1, and divide all that by a minus 1. So this is actually what we call a geometric sum or a geometric series. Now there is a special case for this. If a is actually between 0 and 1, it's not 0, it's not 1, but if it's between there, so it's some fraction, then what we find here is that this sum is less than or equal to 1 over 1 minus a. In fact, if n actually approaches infinity, so if n becomes much larger and larger and larger and larger, this sum actually converges to 1 over 1 minus a. Now to show that, we have to do some calculus, which we're not going to worry about in this class. Okay, but this is what we mean, this is what we call a geometric sum here. Now the next couple of series actually involves arithmetic sums. So this next one is actually pretty common. So we're taking the sum that where I goes from 0 to n and we're adding I. So we're just simply doing 0 plus 1 plus 2 all the way to n. This actually comes out to n times n plus 1 all over 2. And this is approximately n squared over 2 is all we're doing here. And we're going to see this particular one in several different algorithms when we analyze how fast an algorithm runs. But we can just simply say that the sum of numbers 0 all the way up to n is n times n plus 1 over 2, or just pretty close to n squared over 2. Likewise, if I were to do the same thing except I deal with I squared, so 0 squared plus 1 squared plus 2 squared all the way up to n squared, this actually comes out to n times n plus 1 times 2n plus 1, all that divided by 6. And this is approximately n cubed over 3. It's not exactly n cubed over 3, but it's pretty close to it. Now the last two formulas, they're just some very general algebraic manipulations. Just a couple tricks that we can take advantage of. This first one is pretty straightforward. So let's say I have some function, some formula of n. We don't know what it is. We're not worried about it. And what we're trying to do here is we're taking a sum where I goes from 1 to n. So all we're doing here is we're taking f of n plus f of n plus f of n plus f of n. We're doing n times. Well, this just simply comes out to n times f of n. So like, for example, if f of n is x squared, I'm just doing x squared plus x squared plus x squared n times. So this is simply n times x squared. That's all we're doing here. The second one requires a little bit of thought, but when you actually see it, it's not so bad. So here, we're saying that we have some f of I, where I starts at some initial value. It may not be 0, so we call this n0 or n0. So if I say n0, that means n0. Where I goes from n0 all the way up to n, and we want to get the sum of all the f of I. So this would be f of n0, and then the f of the next number all the way up to f of n. Well, what we can do is we can take the sum of all these different formulas where I starts at 1 and goes up to n. So that gives us a much larger sum. And then we take out the first portion of it. So that's what we're doing here. So this minus sigma I equals 1 all the way up to n0 minus 1 f of I, that's saying let's take out f of 1, f of 2, all the way up to n0 minus 1. We're going to take out that portion of the sum from our original sum. So that's all we're talking about here. We'll now take a look at what we call modular arithmetic. So let's suppose we have some number a, and we divide it by n. Whenever we divide two numbers, there must always be some quotient, which we'll denote as q, and there must also be some remainder, which we denote as r. And here, r can be between 0 and up to not including n. So whenever we divide two numbers, there has to be a quotient, there has to be a remainder. So the idea with modular arithmetic is that r is simply equal to what we call a mod n. So a mod n just simply means whenever we take a and divide it by n, there is a remainder. So this mod operator, or what we also call modulus, means that we divide a by n, whatever the remainder is, that's the output of this operator. Now we've seen this before. We have seen this in CS 121. Because whenever we compute a mod n, that's the percent operator in Java. So remember, whenever we did a percent n, that was the remainder of dividing a by n. A mod n does the exact same thing. So at least now you have the mathematical operator associated with the percent sign. So now you know how that ties in together. So there are two properties we want to take a look at with this modulus operator. So the first one is, let's say we have r equal to a mod b. What happens if we add c to our remainder, c to r? Well, r plus c is simply going to be a plus c mod n. You might think it should be a mod n plus c, but since c can actually be larger than n, we have to take the mod n of that as well. So we take a plus c, and then we mod that by n. And then what would happen if we were to multiply the remainder? So if we did something like rd, so we multiply r with d. Well, we did the same idea. It's just simply going to be AD, and then those two are multiplied, and then we take mod n of that.